Hi, welcome to another edition of Calculus 2. Today we are going to start a very important discussion on Maclaurin and Taylor polynomials and approximations. So let's go ahead and see what's the story of this topic. So when you start algebra in middle school, you become familiar with the powers. 1, x squared, x cubed, and so on. And out of these you make polynomials such as 5 plus 6x plus 11x squared minus 3x cubed, and so on. Okay, and then you learn how to handle these. Then you come to pre-calculus and calculus. You see a new crop of functions. You see rational functions, just 1 over 1 plus x. See some radical functions, maybe 1 minus x in radical. Then you come to more advanced functions such as exponential of x, sine of x, logarithm of say 1 plus x, and so on. A question comes up, which is, are these fundamentally new things, or are they like the polynomials you have already studied at the earlier level? Is it possible to make these things look like those polynomials? Well, why would you want to do that? Because those polynomials are so easy to work with. They are built on top of the basic operation, addition, subtraction, multiplication. So if we can convert these to those type of functions, we can get a handle on them, we can approximate them, and so on. Let's go ahead through a short journey. Look at one of these functions. Let's look at sine of x and attempt to make sine look like these polynomials. Let's see how do we go about doing that. So I have a little bit item prepared for you here. So here's my function sine of x. Here's a graph of it, and I want to make this out of the polynomials I have seen. Well, to do this we need a focus point, as if you're going to put a magnifying glass on this thing, and you have to choose where you want to put it at. Let's go ahead, for simplicity, just focus around the origin. So that's where we start at. We ask ourselves, what does this function look like at this location? Well, it looks like it's going up at 45 degrees. So we approximated by that. So if I draw y equal to x, it's pretty close to the graph of sine of x for a while. And of course, then a gap opens up. As we go further out, the gap gets bigger and bigger. The question comes up, can I throw in other terms? You remember the polynomials we had, x squared, x cubed, and so on. Can I throw in other terms to make the gap be smaller? So we might think about, well, how about putting some x squared in it? Let's click this out and say x plus x squared. Well, you see a problem with this. It's kind of lopsided, and the function that we had was symmetric with respect to origin. This one isn't. To be symmetric with respect to origin, we need to keep only odd powers. So even powers are not going to be good, so we are going to clip them off. It's not a good thing to throw them in. Well, let's go after the odd powers. The first of them after x will be x cubed. Let's try to add an x cubed to the mix. So if I have x by itself, this is going to be sensitive. Let's see. Okay, this was our just x. With a being 0, I'm at the level I was before. If I add a term to this thing, so if I go this direction, my gap gets bigger. This is getting worse, not better. So it's better to go toward the negative number. So I go toward negative. I notice that I'm coming close to my sign a lot better than before. Now the question is, what negative multiple should I throw in the mix to make this thing better? Is it minus? It looks like it's getting worse as I go too far to the left. So there is some magic number here that I'll be doing the best. Now, what is that magic number and how we come across it? The approach that we are going to take to come up with how to mix an x and x cube and so on is the following. We are going to try to match the derivatives of the two functions. Okay, the approach we take is that we come to this point, we try to arrange the two functions so that their derivatives will be the same. And then we come across this magic number here. You see, if I have x minus x cubed over 6, I get a very close match between the two functions. Now, where does that coefficient of minus 1/6 coming from? We are going to explain that again. We are going to do that by matching the derivatives. How about the next term? As we said, the even ones are out. We're just going to go look at the odd terms. So here I'm going to throw in 5th power. And it turns out that the best coefficient there is 1 over 120. Now, I graph that, and you notice that it's much better approximation than the previous one. Is that right? The purple one stays close to the sign of x for much longer time. You see it's coming all the way up to here before the gap opens up, but the green one, the gap was forming earlier. Well, we get the idea that if we throw more terms, we can come close to the sign of x, but of course at the cost of making our polynomials get longer and longer. So this is going to be going as far as the 7th power. So 7th power is this black curve here. You notice that all the way up to this pi is actually pretty good and very close to our sine function. So what do we see here? We see a polynomial. It's made out of things that are comfortable for us. These are things we have seen in middle school. We are making an advanced function, this sometimes referred to as a transcendental function, out of things that are comfortable for us. Well, of course, there's no free lunch. There's some price to be paid here. The polynomial getting bigger and bigger. If you want to come close to our original sine function, we have to add more and more terms here. Well, that's going to bring us to that topic of infinite series we studied before. We are adding infinitely many terms in order to reproduce one of these new functions. So that's a common thing among all the functions we are going to study in this section. You have to add up infinitely many terms to reproduce them. What's the use of this? Well, the use is that you have actually a tool for calculating them. All the ingredients here are available to us. We know how to multiply, divide, add, and subtract. So we can create our functions out of these. This is a common trend in mathematics. Once you become familiar with a function, you use it as a base for building other functions. So that is what we are approximating here. Let me show you another example before we go back to paper. Same story holds for cosine of x. Cosine of x is a so-called even function. So this is symmetric across the y-axis. First approximation we can do for it, if you want to focus around the origin, is the flat function of 1. What if we throw in an odd power like x? Well, you notice that it becomes lopsided. It doesn't have the symmetry, so we are going to throw away all the odd powers. Let's go after even powers. So here is, for example, 1 plus x squared. We notice that adding x squared is not a good idea. How about subtracting it? So let's go ahead and go to the other direction. I'm going to decrease a gradually. You notice that we are becoming flat first, then we go to the other side. You notice that I'm coming closer to cosine curve. As I reduce my a at some level, I'm doing a pretty good job of reproducing my function. And that's actually the first approximation. Here we are going to refer to these as Maclaurin polynomials. when we focus around the origin and reproduce our functions around there, what we create is referred to as a Maclaurin polynomial. So here is the first of these things, just exactly what I drew a second ago. Now if I go as far as power 4, I get this one. So this purple curve is doing a better job of approximating the cosine than the green one was. It stays closer to it for a longer time, and the gap is smaller at this level. If I want even better reproduction, I have to throw in more terms. Here is the next one up to level 6. This black curve now staying close to cosine for quite a while. Now the question, the main mathematical question is, well, what are these numbers? That's the major component of the recipe. How do you come up with these numbers? And that's going to tell us how to create these polynomials. These polynomials are referred to again as Maclaurin polynomials. When we do the same thing at some arbitrary point other than the origin, it's referred to as the Taylor polynomials. Let's go back and start this thing. Perhaps the best first thing to do is to start with a polynomial and then reproduce it out of its derivatives and see how that works. So I am going to start with a polynomial, and in order to help you see how the components are built, let me use some parameters so that you just can't follow. Suppose I have a polynomial which is a plus bx plus cx squared plus dx cubed. Let's stop there so that doesn't become too crowded. So first of all, what is f of 0? We said we are going to focus around the origin, so f of 0 of course is a. If I take a derivative of this, what do I get? Of course the constant term goes away, derivative becomes b plus 2cx plus 3dx squared. Is that right? The coefficient becomes a multiple. Well, what is f prime at 0? F prime at 0 is the next number here. You notice that I am recovering these coefficients by calculating the derivatives at 0. Now let's go to the next. Second derivative. Derivative of b will be 0. This is going to be 2c plus 6dx. Okay, 2 times 3 makes 6. And then we see that f double prime at 0, that is 2c. One more round. Suppose I take 3 derivatives out of this function. It becomes 6d. And of course, my third derivative at the origin is going to be just 6d. So who is a? A is f of 0. Who is b? B is f prime of 0. Who is c? C is 1/2 of f double prime of 0. Who is d? D is 1/6 of f triple prime at 0. Do we see a pattern here? Well, of course, these are higher order derivatives of the function evaluated at 0, and they are giving me some multiples of the coefficients I need to recreate my function. So when I want to go ahead and calculate my coefficients, I see the following pattern. Again, one component are the derivatives, and another one are these magic numbers we talked about. So here, well, we don't write it, but it's just 1, and this is 1, 1/2, 1/6. How are they going? How are they created? Well, you had a 3 was brought in front, and it was multiplied by 2 next. So if I had 4, power 4, here there will be a 4, next will be 4 times 3, next will be 4 times 3 times 2, and just that number recovered at the end. So the numbers that we see here, these are really factorial numbers. So what this magic number 6 is really 3 factorial f triple prime of 0. This is 2 factorial f double prime 0. Well, 1 factorial is just 1. And to make the pattern match all over the place, then we have to define this thing as the 0 factorial. So 0 factorial is defined to be 1, and 0th derivative, which means no derivative at all, erase it so we don't cause a confusion, and that is the original function. So the recipe for creating these coefficient is 1 over whatever the power is, a factorial, times the nth derivative of the function. So for example, if I had one more thing here, if I had ex to the power of 4, there would have been a 4ex to the power of 3, and there would have been a 12ex to the power of 2, and that would have given me 24ex, and that would have given me fourth derivative. Now how do we write the fourth derivative? One way to write it is just put so many tick marks, which is kind of hard to see. Another way is to use like Roman numerals, and that gives me now my 24e. Okay, neither of these notations are so great. We are going to adopt another notation, which is how many derivatives you want to take. You put it in a parentheses, so you don't think about it as power. That a number in parentheses means take that many derivatives in this context. So at 0, this is going to be 24e, and if you want to calculate the coefficient e out of this thing, is going to be 1 over 24 of fourth derivative. So fourth derivative at 0, we write it like this, or 1 over 4 factorial of fourth derivative at 0. So if I want to rewrite my function f of x, how would I write it in terms of these coefficients? The very first one is 1 over 0 factorial of 0th derivative of the function at 0. Next one is 1 over 1 factorial of the first derivative of the function at 0 times x. Next one is 1 over 2 factorial of second derivative of the function at 0 times x squared. Next one is 1 over 3 factorial of third derivative of the function at 0 at x cubed, and so on. So here we stopped at 4, but if you had more, well, you just go more. So any polynomial can be created out of its own derivatives at 0. When we focus at 0, we are doing a Maclaurin style, and if we are focused somewhere else, it's going to be the Taylor style. So any polynomial can be recreated out of this summation. How does that summation gets to be created? It is, you take the function, you take the ith derivative of it, calculate it at 0, divide it by I factorial, multiplied by x to the power of I, and add up these things from 0 to wherever you need. So the highest one that you need is the degree of f. Okay, so we can recreate a polynomial like that. Let me again tell you that's exactly what we did here. Let's go ahead, take a look again. For cosine, now cosine wasn't a polynomial, but we are applying the same idea to it. We are gradually throwing in more and more terms to it, and the more terms you throw in, the closer we come to the actual function. So the functions that are not polynomials, then they are going to need infinitely many of these things for us to match them. If they were polynomials, well, the job is going to stop somewhere. That is the difference between a polynomial and the functions that we see in pre-calculus and calculus. So these things, they are not polynomials. They cannot be written exactly like these, but they kind of can be made to look like that. What would be the difference? When we force these things look like polynomials, what we get would be infinitely many terms. And that's why we studied the series before we came to this section. Okay, so again we said when we are doing these things all calculated at 0, we are doing it the Maclaurin style, and if you want to do something a bit more advanced or more general, what is done is referred to as a Taylor polynomial. Okay, let's go ahead and take a standard example and do that. So suppose we take the first function we had was a sine. So consider y is equal to sine of x. Write the Maclaurin polynomial of order, the order is typically captured by n, say of order 6. That is, we are going to go all the way up to power 6 and see what we are going to create. So I start with my function y is sine of x. Let's refer to this thing just as the f of x again, just so that it matches the formulation that we have up here. So what is f0? Okay, that's exactly what we did here. We had a function, we calculated at 0, we calculated its derivative, and calculate the derivative at 0, and so on. And we found our coefficients and we put them in this formula. So that is exactly what we are going to do. So I'm going to take the derivative of this thing. The derivative of sine is of course cosine. Cosine at 0 is 1. Next derivative. Well, what's the derivative of cosine? So we need to know how to differentiate very quickly and accurately. So this is going to be minus sine of x, and the derivative, again, sine at 0 is 0. So we are going to say that this function has a peculiar pattern to itself. So third derivative, we are going to go back to cosine, and its value at 0 is going to be minus 1. When I take the fourth derivative, okay, we agree to write it like this: fourth derivative. Derivative of cosine is negative sine with another minus, becomes plus sine of x. So by the time we come to step 4, we are back where we started. So everything is going to repeat itself. So fourth derivative at 0 is 0. Fifth derivative, so I'm going to write these numbers now. Fifth derivative is so cosine of x. This pattern is going to repeat. So fifth derivative at 0 is just 1. So here, same story. The pattern is going to repeat itself. 0, 1, 0, minus 1, 0, 1. You know, as far as you want to go. The sixth derivative of this thing is going to be minus sine of x, and its value at 0 is 0. So what do we do with these things? The function is going to be approximated by a Maclaurin polynomial. Let's use the capital M for Maclaurin, and we are going to go as far as level 6. How do we write this thing? We start with the first derivative times x to the power of 0 over 0 factorial, that is all ones. Next is 1, then we multiply by x to the power of 1 divided by 1 factorial. So this one, we are going to have lots of numbers that look like each other, but let's keep track of. So this is 1, 2, well, that one turns out to be 0, x to the power of 2 over 2 factorial. 0 here means, well, you don't need to actually bother with it, you don't need to write it. For 3 is minus 1 x to the power of 3 over 3 factorial. Then I have 4, 0 x 4 over 4 factorial. Then I have 5, and I have 6. Well, let's clean this up. Up to level 6, what is surviving is an x, x3, x5, and then of course this one became 0. If I wanted to go one more, it would have been x7. So the polynomial finishes at this level. The x to the power of 6, the coefficient is 0. We don't need to write it. Okay, so if I wanted to, for example, go as far as power 11, how would I write it? Well, now I have to be patient to write so many terms. Okay, so this is the Maclaurin series for the sine function up to including power 11. Okay, so we say if we take this thing and plot it, it's going to look very close to the graph of sine of x. We can use it to calculate sine of x and get a very good approximation and so on. Let's go practice another example of this thing. So suppose we want to write Maclaurin polynomial for cosine of x up to term, again, n equal to 6. So we start with f of x to be cosine of x, f prime is minus sine, f double prime is minus cosine, f triple prime is sine. Now, fourth derivative, we go back to cosine. So the property of sine or cosine is that after 4 iterations you go back to where you were, and f5 again is minus sine. So this is the repeating block, if you wish. f6, we are back to minus cosine. So at 0, what do I have? At 0 it is 1, f prime of 0 is 0, f double prime of 0 is minus 1, triple prime at 0 is 0. Then we repeat. Fourth derivative is 1, fifth derivative is 0, sixth derivative is minus 1. So this is the Maclaurin up to level 6 for cosine. How does that go? Start with very first number that you have. Previously was 0. This is a 1. Next is a 0 that has to multiply by x to power of 1 over 1 factorial. Of course, we don't need to write that. Next is minus 1 that has to multiply by x2 over 2 factorial. Next is 0 multiply x3 over 3 factorial. Next is 1 x4 over 4 factorial, 0 x5 over 5 factorial, and then finally minus 1 x6 over 6 factorial. We clean this up. M6, 1 stays. The other one simplifies to x2 over 2 factorial, x4 over 4 factorial, x6 over 6 factorial. And if you wanted more terms, well, you keep writing. You see that there is a very nice pattern to this. First of all, the signs alternate, plus, minus, plus, minus. For cosine, we only have even exponents. Powers of x are all even numbers. Denominators are just factorials of those numbers in the numerator. If you insist, the very first of it can be written as x to power of 0 over 0 factorial. So that would be making everything look like each other. So for a cosine of x, we are developing a series. What does that series look like? It is x to power, let me write this thing clearly, x to power of 2i, denominator is 2i factorial. Then to indicate odd and even, I can use minus 1 to power of I now. So when I is, for example, 2, the exponent becomes 4, the coefficient becomes positive. When I is 3, the exponent is 6, the coefficient becomes negative. I ranges from 0 to infinity if you want to have a cosine, and it turns out, as we are going to see in the next section, a cosine of x has that series representation. That's going to be the Maclaurin series of cosine of x. Of course, quite a bit of mathematics has to be applied to show that these are actually equal to each other, but right now for the first round of our activities, we are just taking it to be true. You see more advanced treatment of this in your advanced mathematics classes. So here what we have is a Maclaurin series for sine of x. How does that go? This is a particular series that has the exponent 2, let's write I. These are all odd numbers. So odd numbers, I can write it as 2i plus 1. Denominator is that odd number factorial, and here I have minus 1 to power of I again ranging from 0 to infinity. So that is the Maclaurin series for sine of x. Pretty much every function that you see in pre-calculus or calculus has a Maclaurin series. They have to be smooth, have to avoid certain kind of kinks and issues of that type, but aside from that, the functions that you see do have such expansion. Let's go ahead and try one more of these things. For the next example, I'm going to take something with a bit more. So we are going to write Maclaurin series for logarithm of 1 plus x. Okay, so we learned that we are making these polynomials. You can go into these polynomials as many terms as you want. That makes it a series. And so if in exercise they say up to power 3, n equal to 3, and so on, that's where you stop. So in this example, you notice that what we need to do is to be able to calculate the derivatives quickly, essentially. So what is the derivative of this one? F prime of x. Derivative of this, of course, 1 over 1 plus x. And it's going to be a lot easier on us if we write it with a negative exponent, because when I want to differentiate, life will be very easy. Exponent in front times 1 plus x to power of minus 2. Instead of using the quotient rule, this is going to be a lot faster for us. How about the third derivative? Well, third derivative, minus 2 times minus 1 becomes a 2. And then what happens to our exponent? Goes down, so it becomes minus 3. How about the fourth derivative? So fourth derivative, 2 times minus 3 is minus 6 times 1 plus x to power of minus 4. Let's write a few more so that our hand gets used to this process. Fifth derivative, minus 4 times minus 6 is plus 24 times 1 plus x to power of minus 5. But if you wanted to go to 6, so minus 5 to 24 is minus 120 times 1 plus x to power of minus 6. Well, we notice that the numbers, let's write this one, the coefficient is here is 1. 1 minus 1, 2 minus 6, 24 minus 120. These are exactly the factorial numbers, except that they are flip-flopping. Their signs are going from plus to minus. So if I calculated, well, let's start with the function itself. Logarithm of 1. What's logarithm of 1? Everybody remembers that? Logarithm of 1 is 0. F prime. This, when you plug a 0 in it, you just get 1. F double prime. You plug a 0 in this one, well, you get minus 1. Here you get 2. Here, well, let's write it 4. Minus 6. Fifth derivative is 24. Sixth derivative is minus 120. So on it goes. So suppose I want to write Maclaurin up to level 6. What do? Start with that number. Next number times x to power of 1 over 1 factorial. Next number, x2 over 2 factorial. Next number, 2x3 over 3 factorial. Next number, minus 6x4 over 4 factorial. That's for that. Next number is plus 24x to 5 over 5 factorial. Finally, minus 120x6 over 6 factorial. Let's clean up. So m6, this was for logarithm of 1 plus x. Well, this, of course, we don't need to write that. That is just x. Well, let's write the denominator. You see, 1 over 2 factorial. Well, that's just 2. 2 over 3 factorial. That is just 3. Is that right? What is 6 divided by 4 factorial? What do I get? x4 over 4 factorial. 1, 2, 3, 4. This is 3 factorial. 1, 2, 3. You simplify, 4 survives. This is 1, 2, 3, 4. This is 1, 2, 3, 4, 5. You simplify, 5 remains. And this one, of course, this is 1, 2, 3, 4, 5. And this is all the way through 6. So the Maclaurin series here, if you want to write all of them, our exponent is going to be I. denominator is going to be I minus 1 to the power of what? The even ones have to become negative, odd ones have to become positive. One way to do that is to shift your exponent by 1, so that when you start at I equal to 1 for the very first one, obviously you cannot divide by 0, so you have to start at 1, and that one, the coefficient is going to be positive. Next one, at when I becomes 2, the exponent becomes 3, and this becomes negative. So the Maclaurin series for the logarithm of 1 plus x becomes this. Okay, so let's go back and see again what happened. We said we are comfortable with the polynomials. We come across more advanced functions. We want to make them look like polynomials. Well, first we started by taking a polynomial and writing it in terms of its own derivatives. That gave us this idea that a polynomial can be reconstructed from its derivatives. And the question was, can we do the same thing with all the other functions? We tried it for sine of x. So sine of x, we have this Maclaurin series. Cosine of x, we tried this Maclaurin series. And the logarithm of 1 plus x, that was this series. Well, many doors open, and we have many new horizons to look at and answer a large number of questions. You remember, with respect to series, we had the issue of convergence. So when you write something, a series, does it converge or not? That's issue number 1. Issue number 2 is, when it converges, does it actually converge to that function? So more and more questions come up. We're probably going to postpone that to another lecture in the future. This one, it turns out it converges for all x's, no restriction at all. This one always converges to sine of x. Same, we get lucky with the cosine, it converges for all x's, and it does converge to cosine. The nice story doesn't extend all over the place, as we see that some series have limitation on some sort of expiration on them. Do they always work? Well, this one we are going to see that you have to choose x less than 1, and there are more issues with respect to convergence of this one than the others. So hopefully we'll come back to that issue in a later example. So let me leave you with one example to do yourself. Perhaps nicest of all of them, but that is the Maclaurin series for exponential of x. This is a particularly simple one because the derivative of exponential is always just exponential, and the value of it at 0 is always just 1. So what happens is that our job becomes very easy. All over here, everything is just exponential of x, and all over here, everything is just 1. So we quickly come across to the Maclaurin series for this. So 1 plus x over 1 factorial plus x2 over 2 factorial plus x3 over 3 factorial, and so on. You can summarize it like this: x to power of I over I factorial. I ranges from 0 all the way to infinity. This one also has no limitation on convergence. It always converges, no issues. This one, of course, we are going to see later on that x can go as far as 1, but not beyond that. Here, for all x's, and this one is also for, no, we haven't shown that, we're just stating it's a preview of what you're going to see later on for all. Okay, so the homework exercises that you're going to see here is to write the Maclaurin series up to a certain level, and then also more advanced questions on how to use it for approximation, which we are going to do in the next lecture. Until then, good luck and God bless.